Hello, everyone, and welcome back. So we're looking at exponential and logarithmic functions, and in this video, we want to talk about specifically exponential functions. All right, so when we talk about exponential functions, I want to break it down. We want to explore two types of exponential functions, one where we have exponential growth and the other where we have exponential decay. All right, now let's talk about exponential growth first. So exponential growth, let's talk about something like a bacteria culture. Okay, so you have a bacteria that's growing exponentially, and basically its graph would just look something like this. All right, here's my y-axis, my x-axis, and we have a graph that behaves something like this. All right, it's growing exponentially, it grows at a very fast rate, and typically it starts at 0. Or you could have it going to like approaching 0 and not, right? So you can have, typically it's approaching 0. All right, so you're going to have something that behaves like this. It's approaching 0, but never touches 0. All right. And then you can have something that has an exponential decay. And so it could look something like this. Let's copy this. Actually, that's okay. All right, so it could look something like this. Here's my y-axis. Here's my x-axis. And an exponential decay could be something like I don't know, it could be like a radioactive iodine, for instance, that is exploding, and so it's decaying at a very fast rate. So it could be something like that. It could be, and it behaves something like this. All right, so here's our exponential function approaching 0, not touching 0. All right, so it's approaching 0, not touching 0, and it's an exponential decay. So let's say it started at time 0, then I wouldn't include this, but if it's not in terms of time, then it would just look like this. All right, so it's an exponential decay. And an exponential growth, it grows upwards. Exponential decay grows downwards, okay? All right, so it just means that it's growing really fast or it's basically dying out really fast, okay? So what is an exponential function? Now, when we talk about an exponential function, I want us to talk about the main form that it takes. So it takes this form over here, y is equal to a multiplied by bx, where a is not equal to 0, because if a is equal to 0, then we're saying y is equal to 0. So a cannot equal 0. B has to be greater than 0, and b cannot equal to 1, and x is an element of real numbers, and so I have to raise it to a real number, and we can see that the base of this exponential form has to be greater than 0. I'm not looking at negatives. All right, we're talking about positives, and we're going to talk about that characteristic in a minute. But basically, we know that our exponential function has to be taking this form, and so when we're talking about it, we want to just keep in mind that we're saying, oh, okay, so if our exponential takes this form, then these conditions, a cannot equal 0 and so on, have to be met. Okay. All right. So let's have a look at characteristics of the graph of exponential functions. What is that? What are we talking about? And so on. So let's have a look at it. So over here, it says the characteristics of the graph of an exponential function that takes the form of f of x is equal to ab. Well, first we know that it takes this form, but what about that? So the y-intercept, what is going to be the y-intercept? The y-intercept is always going to be a. Now, why is it always going to be a? It's going to be a because if I set x equal to 0, anything to the power of 0 is what? B to the power of 0 is equal to 1. Anything to the power of 0 is going to equal to 1. So our y-intercept is always going to be a. There is no x-intercept. Remember, we said it approaches 0, but never touches. There's an asymptote over here. All right, so it approaches 0, but never touches because we have an asymptote at x is equal to 0. We know that the function itself cannot touch x is equal to 0. okay? So we know that there are no x-intercepts. What about the x-axis is well, we just said it, it's a horizontal asymptote. All right. What about the domain? Now we can see that the function will open outwards in both directions, whether it's an exponential growth or an exponential decay. And so the domain is always going to be XER. X is going to cover all the real numbers. But the range, we can see that the range has to be greater than 0. It doesn't touch 0 because we said that there's a horizontal asymptote there. So we know that y has to be greater than 0, where y is an element of all real numbers. You could actually rewrite it in the way that we're used to. Y is an element of all real numbers such that y is greater than 0. Okay? All right. Now, this is if a is greater than 0. Okay? But if it's reflected, so this is if a is greater than 0, right? Because if I reflect this, right? If I reflect this function that's up here, if I reflect it down here, then we can see that actually y has to be everything less than 0. So if a is negative, and it would be y is an element of all real numbers such that y is less than 0 if a is negative. Okay? All right. Now, let's have a look at some conditions over here. So if we're saying that we have an a that is greater than 0, okay? So if we have a greater than 0, then when b is greater than 1, the function represents what? It represents a growth, okay? Because if I'm talking about a positive number, let's go y is equal to 2, 3 to the power of x. If you plug in numbers in here, you're just going to keep getting bigger numbers, right? So if I go x is equal to 1, that's going to be 3 to the power of 1 multiplied by 2, that's 6. I put another one, x is equal to 2. That's going to be 3 to the power of 2, that's 9 multiplied by 2, that's 18. So do you see how, because they're both positive and they're both greater than, well, a is greater than 0, so it's positive, and b is greater than 1, so it's growing, right? It's going to be growing exponentially, and so if b is greater than 1, then we have a growth. But if b is less than 1, but remember, it has to be positive, right? Remember, b has to be positive. So if b is less than 1, but positive, all right, then the function is going to be a decay. All right. Okay. So let's have a look at some conditions based on b. So over here, when we say that b, the value of b affects the steepness of the graph, absolutely. So if I say, if we can see that over here, when I put b is equal to 3, I went from 6 to 18. Now b is a bigger number, so literally let's just switch this up. Let's go y is equal to 2. Let's go 5 to the power of x. If I go x is equal to 1, y is equal to, let's see, 5 to the power of 1, that's 5 multiplied by 2, that's 10. If I go x is equal to 2, then I have to the power of 2. So 5 to the power of 2, that's 25. 25 times 2, y is equal to 50. Do you see the difference between these two is 40, but the difference between these two is 12. So the bigger the b value, the steeper it is. And let's have a look at what's going on here. So when b is greater than 1, the curve is well, we know rises from left to right, sharply as b increases, right? Because if b is increasing and it's greater than 1, so like we did over here, 3, 5, based on how big the value is, it's just gonna grow like this, or grow a little bit open, or grow a lot open. It really depends on what the b value is, okay? So that depends on what b is. So b is greater than 1 and it's increasing, then we have a sharp rise, okay? So over here, when b is between 0 and 1, so it could be a fraction, it could be like a half, for instance, then it will be increasing. but it's going to be increasing negatively, okay? And so if we're looking at it left to right, then it's basically decreasing, okay? So over here, the curve falls sharply as B decreases. So if I'm going like B is very, very small, so 0.0001, for instance, then we're getting a decrease, but it's a very slow decrease, okay? It's a very sharp decrease at that point if it's 0.0, the smaller it is basically. All right, so let's have a look at this one over here. The value of A affects the vertical stretch of the graph. Choose the correct alternative. All right, so we got to fill this in ourselves. So over here it says that, well, we already know this, right? A is what multiplies by the function f, and we've done this in transformations. So if the function was originally y is equal to b to the power of x, once I put this a inside, that is the vertical stretch. This is a transformed function, right? So you have a vertical stretch of a vertical stretch by a factor of a. And so over here, since we're saying it's a vertical stretch, well, let's have a look at the condition. So when a is greater than 1, so imagine like a is 5, okay? The stretch is a. Would it be an expansion or a compression? Now, if I'm multiplying all my y values by a bigger number, then it should be getting bigger. And so this is going to be an expansion, okay? And over here, when a is in between 0 and 1. So think of it as a fraction, like you're multiplying by a fraction or like 0.001, then you're making it smaller. You're making the value of the function smaller. And so this stretch is going to be a compression. Okay. And if A is negative, all right, so this has nothing to do with stretch or compression, but if A is negative, so A is less than 0, then we have a reflection. Where are we going to reflect? Well, I'm multiplying all my y values by negative, and so if I'm up here, I'm reflecting about the x-axis going down there, right? So if A is negative, then I reflect about the x-axis. Okay? All right, everyone. So this is pretty much it covering everything you need to know about exponential functions. Please join me in the example videos where we're going to do a lot of examples on exponential functions together, okay? I'll see you there. Bye.